Alright, let's go. Number 10. The Magellanic Stream Contamination. Andrew Fox at the Space Telescope Science Institute was not trying to find anything unusual. He was measuring gas flow, tracking how much hydrogen the Milky Way pulls in every year to keep making new stars. Routine bookkeeping. The kind of paper that normally gets cited twice and forgotten. Standard galactic chemical evolution says gas stripped from a satellite galaxy should carry that satellite's chemical fingerprint. The Magellanic Stream, a ribbon of gas 200 degrees long, torn from the large and small Magellanic Clouds by the Milky Way's gravity, should be chemically uniform with its source. Predictable, traceable, explainable, it isn't. In 2023, Fox and his team, using the Hubble Space Telescope, confirmed the Milky Way is accreting the stream at roughly 0.4 solar masses a year. But buried in the data was something else. A 2022 paper led by Yanbin Yang identified nitrogen-enhanced regions inside the stream, abundance ratios that do not match the known stellar populations of either Magellanic Cloud. Explanation 1. Contamination from an unrelated foreground cloud. Ruled out the kinematics match the stream, not a foreground object. Explanation 2. Enrichment from Milky Way disk gas mixing in. The geometry doesn't support it, the anomalous regions sit too far from the disk. Explanation 3. An undetected third progenitor, a dwarf galaxy that no longer exists in visible form, contributing its own chemistry to the stream before being torn apart entirely. No trace of it has been found. You are, in this exact moment, made partly from hydrogen the galaxy hasn't finished eating yet. Some of what falls onto the Milky Way tonight came from something that isn't there anymore. What galaxy contributed chemistry to gas we can still see, when the galaxy itself left no other trace? The stream is being consumed. What consumed it first is another question entirely. Number 9. The hypervelocity ejection problem. In 2005, astronomer Warren Brown at the Harvard-Smithsonian Center for Astrophysics was surveying faint blue stars in the outer halo, trying to catalog stellar populations far from the galactic disk. He wasn't hunting for anything exotic. He found a star moving at roughly 700 kilometers per second. Normal stellar velocities in the Milky Way top out around 200 to 300 kilometers per second, bound comfortably by the galaxy's gravity. A star moving that fast should be impossible unless something extraordinary accelerated it. The standard model has one answer: a close encounter with Sagittarius A, the supermassive black hole at the galactic center. Brown's star was moving fast enough to leave the galaxy. Permanently, since 2005, roughly 30 confirmed hypervelocity stars have been catalogued. In 2019, a team identified S5HVS1, clocked at 1,755 kilometers per second, the fastest ever confirmed, its trajectory tracing directly back to Scirré. The mechanism proposed by Jack Hills in 1988, a binary system approaches the black hole, one star is captured, the other flung out at escape velocity, fits the data. Explanation of the anomaly stops there, because the anomaly isn't the mechanism, it's the count. Current models predict a specific ejection rate based on binary capture statistics near Scirré. The observed population is consistent for some stars, inconsistent for others. Several hypervelocity candidates have trajectories that don't trace cleanly back to the galactic center at all, and no alternate origin has been confirmed. These stars are in transit right now, crossing the galaxy toward its edge, carrying no warning system, no light speed announcement of their arrival. A star moving at 1,755 kilometers per second would disrupt any planetary system's outer bodies in minutes, without a single year of notice. Something at the center of our galaxy is firing stars outward on a schedule we can only partially explain. What determines which ones we can trace, and which ones simply appear already in flight? The center of the galaxy is not calm. It is a mechanism, still firing. Number 8. The Halo Disturbance. In 2018, the Gaia satellite released its second dataset, 1 billion stars, positions and velocities measured with unprecedented precision. No one on the Gaia team was searching for a disturbance. They were building a catalog. A map. The standard assumption about the galactic halo, the diffuse, sparse cloud of ancient stars surrounding the disk, was that it should be smooth, virialized, settled after billions of years. Old stars on old randomized orbits. A quiet outer suburb of the galaxy. The halo is not quiet. It is moving in ways that shouldn't have survived this long. In 2019, astronomers Vasily Belokurov and Sergei Kopasov identified what they named the Gaia sausage, a population of halo stars on highly radial, elongated orbits, the fossil signature of a major merger roughly 10 billion years ago. Then in 2020, further analysis found the halo has a rotating component inconsistent with a smooth, settled structure. In 2021, researchers proposed that the Large Magellanic Cloud, itself mid-collision with the Milky Way, is actively driving a gravitational wake through the halo, causing the galactic center itself to oscillate. Every explanation converges on the same uncomfortable point. The disturbance is not ancient history settling into place. It is current. Ongoing, the LMC is still falling, the wake is still propagating, and the center of our galaxy, the fixed point everything else is supposed to orbit, is measurably moving because of it. The floor of the house is not solid. It has been rocking, slowly, the entire time you've been standing on it. If the center itself drifts, what exactly are our galactic coordinates measured against? Number 7. The Fermi bubble origin. In 2010, Doug Finkbeiner at the Harvard-Smithsonian Center for Astrophysics was working through Fermi gamma-ray space telescope data, trying to characterize diffuse background gamma-ray emission. Cleaning noise out of a map, essentially, he found two enormous lobes instead, rising 25,000 light-years above and below the galactic plane. Centered precisely on Sagittarius A. Standard models of a quiescent galactic center predicted no large-scale gamma-ray structure of this kind. SCIR A today is faint, barely accreting, gravitationally sedate. Whatever inflated these lobes should not have been possible under current conditions. The bubbles contain approximately 10 to the power of 55 ergs of energy. More than 100,000 supernovae combined. And they are still expanding, at roughly 1,000 kilometers per second. Explanation 1. A past quasar-like accretion phase at SCR-A, when the black hole was feeding violently. Explanation 2. A massive burst of star formation near the galactic center, whose collective stellar winds and supernovae inflated the structure. Neither fully accounts for the energy budget or the sharp-edged bubble geometry. In 2020, X-ray data revealed even larger Erosita bubbles, extending 45,000 light-years, potentially linked to the same event, meaning whatever caused this was bigger than either explanation alone allows for. The source went quiet. The consequences did not. The shockwave from an event that ended millions of years ago is still moving outward through the galaxy, and we are timing our observations from somewhere inside its blast radius. What kind of event releases that much energy, stops completely, and leaves the sky still ringing from it a few million years later? Number 6. The Sagittarius impact history. In 2020, astrophysicist Toms Ruiz Lara at the Instituto de Astrofísica de Canarias was reconstructing the Milky Way's star formation history, building a timeline from Gaia data on stellar ages and chemical compositions. A demographic study. Not a search for a cosmic collision. The standard picture of galactic star formation is a slow, roughly continuous process, gradually declining over billions of years as gas is used up. Smooth, gradual, predictable, entry by entry, star by star. Ruiz Lara's reconstruction showed 3 sharp spikes instead. Star formation bursts at 5.7, 1.9, and 1.0 billion years ago. Each spike lines up, almost exactly, with a known passage of the Sagittarius Dwarf galaxy punching through the Milky Way's disk. The Sagittarius Dwarf, currently being torn apart by our galaxy's tides, its debris stretched into a stream that wraps entirely around the sky, has hit us at least 3 times. And the timing places our own sun's formation inside the window of the second or third impact. There is no remaining alternative explanation in the literature that accounts for all three peaks without invoking the Sagittarius passages. Internal disk instabilities were proposed and failed to reproduce the precise timing. External gas accretion alone failed to reproduce the burst intensity. The Dwarf galaxy is the only mechanism that fits. You may exist because a smaller galaxy crashed into ours, more than once, and compressed a gas cloud hard enough to ignite a stellar nursery. Sagittarius's core remnant is still out there, still bound, on a trajectory that returns it through the disk again in roughly 10 million years. If your solar system's birth was a collision byproduct, what does the next collision produce? Number 5. The warped and precessing disk. In 2019, a team led by Zhou and Chen at the Chinese Academy of Sciences was mapping classical Cepheid variable stars across the Milky Way using Gaia and WISE data, simply trying to build a precise three-dimensional map of the galaxy's outer disk. A cartography project. Standard galactic models treat the disk as flat, or at most gently and symmetrically warped in a fixed static shape, a S-curve bent slightly up on one side and down on the other, held stable by the halo's gravity. Chen's team found the warp is not static. It twists, and the twist itself rotates around the galactic center over time, like a slowly turning saddle, completing a full precession cycle on a timescale of hundreds of millions of years. The 2019 paper, published in Nature Astronomy, measured the amplitude of the warp increasing with distance from the center, reaching roughly 15,000 light-years of vertical displacement at the outer edge, and confirmed the whole structure precesses rather than sitting fixed in space. Proposed causes: torque from the misaligned dark matter halo, partially supported. Doesn't fully match the precession rate. Gravitational interaction with the Magellanic clouds contributes, but calculations undershoot the observed twisting speed. Intergalactic gas flow pressure on the outer disk, plausible, unconfirmed, no direct detection of sufficient flow. No single mechanism accounts for the full motion. The outer edge of the disk you live inside is not a fixed shape. It is warping and twisting on a slow, geological clock, and no explanation currently accounts for the speed at which it turns. What is massive enough and asymmetric enough to keep an entire galactic disk permanently off balance? Number 4. The Radcliffe Wave. In 2018, astronomer Alyssa Goodman and colleagues, including Ju Alves and Catherine Zucker, were building a precise three-dimensional dust map of the solar neighborhood using Gaia data, cataloging nearby star-forming clouds that astronomers had studied individually for a century, under the name the Gould Belt. The standard assumption, dating back over 100 years, was that these star-forming regions form a roughly circular ring around the Sun, tilted slightly relative to the galactic plane. A belt. A closed loop. It is not a ring. It is a wave. Published in Nature in 2020, the team's reconstruction showed the clouds actually form a single, continuous, undulating filament nearly 9,000 light-years long, oscillating above and below the galactic plane like a slow-motion sine wave, with an amplitude of about 500 light-years. They named it the Radcliffe Wave. The Sun currently sits close to it, and is estimated to pass through the structure roughly once every 30 million years, based on its orbital motion. Explanation 1. A passing dwarf galaxy or dark matter substructure perturbed the gas into an oscillation. Unconfirmed, no culprit identified. Explanation 2. It's a resonance pattern from spiral arm dynamics. Doesn't fully reproduce the observed wave amplitude. The oscillation's cause remains, in the team's own words, unexplained. For 100 years, astronomers looked at the star-forming clouds nearest to Earth and described the wrong shape entirely. We were living next to a wave and mapped it as a ring. If our basic geometry of the nearest structure in the galaxy was wrong for a century, what does that imply about structures we've never mapped directly at all? Number 3. The local bubble expansion. In 2022, Catherine Zucker, then at the Center for Astrophysics, Harvard and Smithsonian, was mapping young stars and star-forming regions in 3 dimensions around the Sun, refining distances using Gaia parallax data. Cartography again, a project to place familiar star-forming regions on an accurate map. The standard assumption was that the sun sits in a low-density cavity of hot gas called the local bubble, roughly 1,000 light-years across, and that nearby star-forming regions are scattered around it more or less independently, unrelated to the bubble's structure. Zucker's team found that nearly every young star-forming region within a few hundred light-years of the sun sits precisely on the surface of the bubble, not scattered nearby, on the shell itself. The 2022 paper, published in Nature, dated the bubble's origin to a cluster of supernovae that went off starting roughly 14 million years ago, carving out the cavity, and showed the bubble's surface is still expanding today at around 6 kilometers per second, sweeping up gas and triggering new star formation exactly where it currently sits. There is no remaining serious alternative to the supernova-driven shell model at this point. Earlier proposals treating nearby star formation as independent of the bubble were directly falsified by the 3D reconstruction. The open question isn't the mechanism, it's the timing. The sun is inside this bubble right now. It has been for an estimated several million years, and the shell walls are still moving outward as you watch this. We are sitting inside the wreckage of ancient supernovae, and the wreckage is still expanding around us in real time. How close was the sun to that original blast when it went off? Number 2. The Monoceros Ring. In 2002, astronomer Heidi Newberg at Rensselaer Polytechnic Institute was analyzing Sloan Digital Sky Survey data, searching for structure in the outer stellar disk, a fairly routine stellar census project. Standard galactic models predict the outer disk should fade smoothly into the halo, stellar density dropping off gradually, with no sharp features. No coherent rings, nothing structurally distinct. Newberg's team found a ring of stars circling the galaxy in the outer disk at roughly 100,000 light-years from the center, coherent enough to trace across a huge span of sky. It didn't fade smoothly. It was a distinct structure with a name, the Monoceros Ring. In 2004, a separate team led by Rodrigo Ibarra identified the Canis Major overdensity, proposing it as the core remnant of a dwarf galaxy currently being torn apart, with the Monoceros Ring as its tidal debris, directly analogous to the Sagittarius stream. Explanation 1. The dwarf galaxy remnant model fits the stellar population data reasonably well, but has never produced universal agreement. Some researchers argue Canis Major isn't a real dwarf core at all, just a dense patch of the Milky Way's own warped and flared outer disk. Explanation 2. The disk warp model explains the ring's plane alignment but struggles to explain its distinct stellar population age and metallicity. More than 2 decades later, astronomers still cannot agree whether this ring is the corpse of a cannibalized galaxy or simply our own disk folding on itself. 20-plus years, full sky surveys, thousands of citations, and the field still cannot say definitively whether this ring is our galaxy or someone else's remains. If we cannot tell our own disk apart from a dead galaxy's debris at 100,000 light-years, how confident should we be about anything further out? Number 1. The vertical ringing of the disk. In 2012, Lawrence Widrow at Queen's University and collaborators noticed an oscillation in the vertical positions and velocities of stars near the Sun, published in the Astrophysical journal Letters, a small statistical anomaly in what should have been settled disk kinematics. Standard disk dynamics assumes the Milky Way's stellar disk, after billions of years, should be relaxed. Stars moving up and down through the plane in smooth, damped, unremarkable orbits. A settled structure. No memory of past disturbances. In 2018, using Gaia's second data release, astronomer Teresa Antoja and colleagues found something far more dramatic than Widrow's original signal. A clear spiral pattern in the position-velocity space of disk stars near the Sun, visible as a snail shell shape when plotted. Astronomers now call it the Gaia phase spiral. Published in Nature, Antoja's team showed the pattern's shape indicates the disk was gravitationally kicked, hard, somewhere between 300 and 900 million years ago, and has been vertically oscillating, ringing, like a struck bell ever since, still not fully damped out. proposed triggers a close passage of the Sagittarius Dwarf galaxy. The same object responsible for the star formation bursts and the tidal stream circling the sky. This is currently the leading candidate, but the exact timing and number of passages required to produce this precise spiral shape remains actively debated, with competing models proposing different impact histories that all partially, but not completely, reproduce the observed pattern. The disk you are standing on, right now, at this moment, has not stopped vibrating from an impact that happened before humans existed. Every star near the Sun, including the Sun itself, carries the fading signature of that collision in its motion. A bell does not ring forever. This one has been ringing for hundreds of millions of years. When does it finally go quiet? And were we here for the strike, or only for the echo? The Magellanic stream carries chemistry from something we can't find. Stars are fired from the center on schedules we can't fully predict. The halo drifts, the disk warps, twists, rings, and has been struck by the same intruding dwarf galaxy again and again across billions of years. None of this sits at the edge of our knowledge. It sits at the center of it, inside the best-mapped galaxy in the universe, using the most precise stellar catalog ever built. The anomalies didn't survive because we haven't looked closely enough. They survived because we have. The universe is not confused. It has been doing exactly what it does, in plain sight, the entire time. We are the ones still working out what we're looking at. If you want to see more videos like this, click the video on screen now.